Hello everyone. In this session we'll see another question on expansion using Leibniz method. So it says prove that e to the power of cos inverse of x is equal to e to the power of pi by 2 1 minus x plus x square by 2 minus 1 by 3x cube plus 5 by 24 x to the power 4 and so on other terms. So let y is equal to e to the power of cos inverse of x, and differentiating with respect to x, we have y dash, let's say y1 is equal to e to the power of cos inverse of x into minus 1 by under root of minus 1 by x square. So overall we can write y1, that is y1 dash, is equal to, so this e to the power of cos inverse of x is nothing but y divided by, and minus is also there, under root of 1 minus x square, and on squaring we'll get one minus x square y1 square equal to y square. Now differentiating this both the sides with respect to x, we'll get for this 1 minus x square into y1 square. So let's do the UV differentiation. 1 minus x square and differentiation of y1 square is 2y1 into y1 dash. So let's say this y1 dash is actually y2. So 2y1 into y2 minus y minus, because differentiating the u part. So minus 2 times of x into y1 square equal to, on the other side, 2y into y dash. So y dash is y1. So 2y y1. And you can see that there is one y1 common in all the terms. So rewriting it as 1 minus x square into, let's say 2 is here, and y2 minus 2x y1 equal to 2y. Of this we can also take out this 2 common. So why not to write it as 1 minus x square y2 minus x y1 equal to y. So after this, now we can apply Leibniz theorem and find some of the general term. So applying the Leibniz theorem and differentiating n times, we will have, for the first term 1 minus x square y2, we will be getting nth derivative of y2. So y2 is actually y double dash. So it becomes 1 minus x square into yn plus 2. So it was already a second derivative, and nth derivative over it is n plus 2. plus n times of first derivative of 1 minus x square, which is minus 2x, into n minus 1th derivative of y2. So this is yn plus 1. Again minus 2, that is the second derivative of 2x, into n minus 1 divided by 2 into n minus 2 derivative of y, which is n. So this was about the first term. The second term, minus xy1, will be minus of, so nth derivative of y1. y1 is y dash. So yn plus 1. Now we can find first derivative of x, and after that we won't have any other term because it will be 0. So x differentiation will be 1. So 1 into n into yn, because this is n minus 1th derivative of y1. So that is n minus 1 plus 1 equal to yn. And on the other side, which we can take on the same side also possibly, so this equal to y can be taken on the same side and becomes minus yn equal to 0. Of course we can rearrange the terms as per the requirement, and we see for yn plus 2 we will have only one coefficient, which is 1 minus x square yn plus 2. For yn plus 1 we can have more terms, so let's write all those. Yn plus 1 will come from here, so this is minus 2nx. The another one comes from this term, so this is minus x. So this was about yn plus 1. And for yn, this is also negative, and this is also negative, this is also negative. So let's take minus outside. We can write 2 and 2 gets cancelled, n square minus n. From here we will have minus 1 minus of n, and then this minus and minus becomes plus, and then minus 1 yn equal to 0. So that is 1 minus x square yn plus 2. We can take minus and x both common, so it is 2n plus 1 yn plus 1, minus this n and minus n gets cancelled, so minus n square taking minus also common. So if we are taking minus also common, this is going to be plus 1 times of y1 equal to 0, right? So overall this is one general term, and we can generalize it more by taking the exceptional case for x equal to 0. So for x equal to 0, this term 1 minus x square will be left with only 1, so yn plus 2. The next term is having x as a factor, this one, so the entire terms becomes 0 because of x equal to 0. This is having no x factors, so it will be minus of n square plus 1 times of yn equal to 0. So this is the condition for x equal to 0. From here we are into the special case of x equal to 0. Now moving back to all the terms we have found, we can try finding the values for x equal to 0. This is our y, so y of 0, we can find it from here. E of cos inverse of x will be e to the power of pi by 2. Next term is y1. From here we can take the y1. y1 0 will be minus y. So what is minus y? Minus y we have already seen, it is e to the power of pi by 2. So minus e to the power of pi by 2, and denominator will be 1. So let's leave it like this only. Next is our term y2. So we can take y2 from here. y2 at 0, x equal to 0. So this 1 minus x square will become 1. X term will become 0 and it will be only y. So this becomes e to the power of pi by 2 because y in the sense of y of 0, and y of 0 we have already found to be e to the power of pi by 2. Now we can move for the general terms. Let's say for in the case of x equal to 0, continuing, if n is equal to 1. So you'll have yn plus 1 equal to 3 equal to, like this can also be written as yn plus 2 equal to n square plus 1 times of yn. So this becomes n. So 1 plus 1, this is 2 into y1. And we have found y1 to be e to the power of minus e to the power of pi by 2. So this becomes minus 2 into e to the power of pi by 2. Similarly, n equal to 2 gives n plus 2, which is 4, equal to 2 square plus 1 into y2 because that is n. So this is 5 times of y2, and y2 we have found to be e to the power of pi by 2 above. So this, if it is n equal to 3, y5 because n plus 2 becomes 3 square plus 1 and y3. So y3 is already found here. This is y3 and this is 10. So this is going to be minus 20 times of e to the power of pi by 2. So on, we can find other terms also. Now of all the terms we have found, the Maclaurin series can be given as f of x is equal to, which is y, equal to y of 0 plus x times of y1, y1 in the sense of y dash, y1 of 0 plus x square by 2 factorial y2 0, y2 in the sense of y double dash, plus x cube by 3 y third derivative, and so on. So y of 0 we have already found it is e to the power of minus e to the power pi by 2, and y1 is minus e to the power pi 2, y0 is e to the power of pi by 2. So we are putting the values we have already found. Y of 0 is e to the power of pi by 2 plus x times of minus e to the power of pi by 2 plus x square by 2 factorial into e to the power of pi by 2 plus x cube by 3. y3 we have found to be minus 2 e to the power of pi by 2 plus, let's say, the other term x to the power 4. This is 3 factorial 4 factorial into 5 e to the power of pi by 2, and or other higher terms, but we may not need it as per the expression to be proved or expanded. So why not to take e to the power of pi by 2 common, and we will be left with 1 minus x plus x square by 2 minus x cube by 3 plus 5 by 24 x to the power of 4 and other higher terms. So this is nothing but our own expression, which was y equal to e to the power of cos inverse of x. So this is the expansion we were looking for, and we have achieved it. So this is how we are using the Leibniz method for the expansion of the function.